So, good morning everyone. Nice to see so many of you here. My name is Maarten Mulders. Welcome to my talk on SSL or TLS for mortals. I work at a company, InfoSupport, Dutch-Belgian company, and we typically do awesome sauce in what we do, the projects, the technology that we use. But today, transport layer security. Who thinks this is awesome? That's not so many hands, a few hesitants. Who thinks this is headache material? A lot more hands, actually. Excellent. This is very good. Exactly what I was hoping for, basically. So, what do you typically do when you are greeted with stack traces like these? I mean, they're so big. They don't even fit in the box. What do? Panic. Good reaction. Stack Overflow. Always a good thing. What I see that many people do is they go to their coworker, that one specific coworker, who, well, he knows something about security and some things about certificates. Maybe he can help me out. And of course, it's good to ask for help. But wouldn't it be even better if you knew the basics yourself and were able to do the basic troubleshooting yourself and actually understand what's going on? If you feel, yes, that's what I want, then please stay here. So, why is this actually important? The thing is, we are building more and more systems nowadays that are connected to other systems. You could call them microservices if you wish, but even before the microservices age, when we were doing service-oriented architectures, we also had a lot of connections between our systems. And we usually want these connections to be reliable, of course, but also to be secure, in the sense that no one can eavesdrop on our connections and actually see what those systems are exchanging. And now, in the age of clouds and public clouds spanning the whole globe, and systems being deployed across those clouds, and even connecting between various clouds, between on-premise systems and public cloud systems, this becomes even more and more important to do it the right way. And that's what we're going to discuss today. So, maybe the first question that we should try to answer is, what is transport layer security? Well, you might have seen this OSI model. And the OSI model tells us that if we want to do encryption, this belongs there, in the presentation layer. Which says that if two systems want to exchange data in a secure way, they should take care of that themselves. So you're building an application, and somewhere in your application is code that takes care of encrypting some data, and in the other system there's code that takes care of decrypting the data. Of course, this works if you do it correctly, but there's many things that you can actually do wrong if you roll your own encryption. But even more important, if we take this approach, we're doing it all over and over again. Because every time we want to send some data, we need to encrypt it, and every time we need to decrypt data, we need to do it ourselves and build it into our applications. And now transport layer security basically says we'll push this responsibility down to the transport layer, hence the name. It isn't rocket science. So if we can rely on a transport layer that has encryption built in, we can be sure that we are reusing proven implementations and don't need to reinvent that wheel every single time again. In the end, this should save us as application developers time, should save us money in the end, and we would all be happy. Now, a brief history, because what is a talk on a major topic like this if there's not a slide on the history of the concept? It all started with SSL 1.0, which was released, well, actually not released. It was described by Netscape. Who ever heard of Netscape? Just to see how old we all are. Oh, that's excellent. Excellent, Netscape. So they came with the first specification of secure sockets layer, as they used to call it. Well, they made up version 1.0, but it was so unstable and so immature that they never dared to release it. In 1995, they described secure sockets layer version 2.0, and this was considered good enough to actually use in production systems. 1995, and it lasted until 2011. And then security researchers published their Poodle attack, which actually rendered SSL 2.0 unusable, not secure, not to be trusted. SSL 3.0 was released in the meantime, 1 year later, which was also vulnerable to the Poodle attack, but that was actually discovered later in 2014. Then in 1999, the first release of TLS, Transport Layer Security 1.0, came out, which was basically the same as SSL 3.0, with a few small differences, not really worth mentioning it SSL 4 or something, but big enough to give it a new name somehow. It was released in 1999, but also vulnerable to the Beast attack. Vulnerable to the Beast attack, so not to the Poodle attack, but the Beast attack. So any of those protocols, please, if you use them, stop doing that immediately, because there's published attacks that actually render it unusable. In 2006, TLS 1.1 was released. In 2008, TLS 1.2 was released. And last year, TLS 1.3 was released. All of these can be considered secure, but please mind you, the fact that no attack has been published doesn't mean there is none. It's just that nobody actually wrote about it. There might be people or governments or institutions that are actually capable of successfully attacking those protocols. We just don't know. It's the same as with software. We can describe that it does certain things, but we can never be 100% sure that there are no bugs in it. So for the remainder of the talk, I'll try to stick with TLS, or Transport Layer Security, and let's forget about SSL. But the thing is, many documentations still mention SSL. And, well, that's why we sometimes intermix the two, but they are not the same. So now you might be wondering, okay, that's all cool, but why do we actually need something like Transport Layer Security? It's time for a little demo. On this screen, I'm running a packet sniffer. Who's familiar with packet sniffers? Majority, excellent. I'm not going to explain this one. By the way, is the font readable, even in the back? Yes, excellent. Thank you for your feedback. So, in this screen, I'm going to invoke a web server that's running on my machine. The packet sniffer is running on the loopback interface, so I should be able to intercept all traffic that comes by. I'm using CURL, which is a command line HTTP client. I'm giving it the verbose switch to actually be a bit more verbose about what's going on, and I'm just accessing localhost. What do we see here? We see that we get a response with HTTP 200, and we get a lorem ipsum and the rest of the text, which I'm too lazy to copy-paste. Now if we go back to our packet sniffer, and we scroll up a little bit, we can actually see get HTTP 1.1, localhost, and we can actually also see the response HTTP 200 OK, and there it is, lorem ipsum and the rest. If you don't have Transport Layer Security, anyone who is able to sniff on the packets that your systems transmit will be able to read along. And now imagine that you are using internet banking and your internet banking system would not use HTTPS, and you'd be on an open Wi-Fi, for example, in the hotel or in the train. People can sniff your packets. People can actually see the content that you're posting into your login screen. Usernames, passwords, all the like. This is what we're trying to address with Transport Layer Security. Bless you. So what are we going to do to prevent all of this? We need three things. The first thing that we need is public and private key encryption. The second thing that we need is certificates. And the third thing are certificate authorities. Let's dive into this. First of all, public and private key encryption. This can be pretty hard stuff. So I pulled up some diagrams that I hope everyone is able to understand. Everyone who has ever bought furniture at a blue-yellow Swedish company, which name I shall not be mentioned today, should be more or less familiar with this diagramming style, right? So what do we see here? We see a safe. And this is actually a very special safe because the lock is capable of receiving 2 keys. With 1 key, we can actually open the safe. With the other, no, I should say that differently. With 1 key, we can turn the lock in one direction, and the other key will turn the lock in the other direction. And this 1 key is marked with a globe, which means it's a public key. And as we can see in the second step of this very difficult diagram, we can actually share that key. Every one of you can have this public key of mine. It's no problem because it's public. You're more than welcome to have it. There's 1 key that's not public. That remains with me. It's the private key, and that's why my face, including a hat, is depicted on it. Now, what can we do? Imagine I have a letter. It's a love letter, so it's more or less confidential. Don't want everyone to read along. I'll put the letter in the safe, and I'll use my private key. No, I'll use the public key, excuse me please, the public key of the receiver to actually close down the safe. Now it's closed, no one can open it anymore, except for the person who has the private key with the hat on it. So if you want to send a letter to someone, you pick the public key of that person and use that to lock the safe. And now you can actually put the safe on whatever transport mechanism you like. It can be a truck, it can be a pigeon, it can be anything. Well, pigeons typically don't carry locks, but the safes, but still. You can use any transport mechanism. It can be unsafe, it doesn't really matter, because the lock's on there and no one's going to open the safe unless they have the private key. Now, the receiver will pick the safe of the truck, use the private key to open the safe and see that there's a letter inside and read it, and will probably be happy because it's a love letter in this picture. So all's good there. Of course, this is not what happens in reality, because in reality, public-private key encryption uses a lot of mathematics. So let's go one step deeper and dive into that. Most public-private key mechanisms that we use nowadays are RSA or variations thereof. And I'm going to explain to you on a high level how RSA works. The first step is that we select 2 prime numbers. Let's call them P and Q. And the only requirement that we have is that they are prime numbers. In this example, I'm picking 11 and 17. Next, I'll calculate the product, which is a very simple calculation. P times Q equals 187. Now I'm going to select some random number, and the only requirement is that it's smaller than the product. We'll call that number E, and in this case I'm, well, 3. Let's just use the number 3. And now here's a small mathematical puzzle for you. Please give me a value D for which it is valid, for which holds that D multiplied with E minus 1 modulo P minus 1 multiplied with Q minus 1 equals 0. If you have a little bit of mathematics in your brain, and I think most of us have, we can see that there's one unknown in the equation, so we can actually solve this equation. It requires a few steps, but it isn't that hard. Let's say that, well, we know E, so we can fill in the number E for 3. We know P and Q. 10 times 16, equation should still be 0, the outcome should still be 0. D times 3 minus 1, let's say that it's 320, modulo 160, still equals 0. So then we say, okay, there was a minus 1 in this, so actually it's 321 minus 1 equals 320, modulo 160, still 0. And then finally, let's say 107 multiplied with 3 by 3 means 321, minus 1, etc., etc. So what we see is that D equals 107. Now, what is important to note is that if I would have selected another random number, and it's a random number so I can select anything, we will have another outcome for this equation. It might, for example, when E equals 75, D would be 183. This is all good. This isn't too much mathematics. But now what if we would not know P and Q? What if those two values are unknown to us, but we do know their product? So we do know that P times Q equals 299 in this example. We do know the random number, which is 5. And again, we have this question of finding D for which the equation holds. Can we do this? The answer is there is no algebraic way to do this because we have too many unknowns. We can do some trial and error. But that's only feasible if the numbers aren't too big. If we do know P and Q, by the way, for example, we know that they are 13 and 23, it becomes trivial to calculate D again. But as I said, this only works for small numbers, the trial and error approach. If P and Q, the prime numbers that we took in the very first step, are large enough, their product will be even larger, because it's a multiplication. And finding the two prime numbers will go towards infinity when it comes to the time that we need to find them, by just using trial and error. And infinity still is a pretty long time for humans to cover. So we can be, well, more or less sure that we can keep it this way. We can actually distribute P and Q. We can actually distribute the random number. As long as we keep P and Q for ourselves, the product of them, P multiplied with Q, is open for anybody to know. This is the public key. The individual values for P and Q are my private key, and I'm not distributing those. Now, when we apply this mechanism to, for example, encrypting some text, let's say that our letter starts with the G. We can say, okay, G is the 7th letter of the alphabet, so P times Q equals 187, as we saw. E still is 3, and we want to use the input 7, which maps to the letter G. Now what we can do, we calculate the input to the power of E, so that's 7 to the power of 3, which is 343. We take the modulo with 187, which gives us 156. Now 156 is the outcome, and if we want to decrypt that, again we should know the individual values for P and Q. And by knowing those, we can derive what the value is for D, and then we can decrypt this encrypted message of 156. What we do, we calculate 156 to the power of D, which is 107, and this is approximately 4.6 with 234 zeros behind it. Yes, this is rounded. This is not exact. Your calculator on your phone isn't going to do this for you. Excel doesn't do it for you, so you really need to write some code if you want to verify this, but please trust me on this one. It's approximately that number. It's very big, but we don't care, because the next thing we're going to do is we're going to divide it by 187 and see what the modulo is of that, which is 7. That's magic, because 7 was our input number, which was the letter G. So by doing these steps, we can actually transform our input, the number 7, to a ciphertext, which is 156, and using other private key data, we can actually go back to our input, which is the number 7. We have no fairy tales this time. So this is all fine and good. Now when two systems want to connect to each other, of course, they need to, well, get acquainted. If I've never talked to any one of you before, we probably first need to verify which language we both speak. We're in Belgium, people speak many languages here. I could try English, which is probably fine, but maybe you speak Dutch as well, like me. So there's kind of a handshake in this process, and computer systems do the same. So imagine that we have a client program that wants to talk to a server. The first thing is that the client says hello. Clients are very polite. And the server will respond with another hello, because also servers are very polite. The server will then present its certificate, and we'll see in a few minutes what that is. And will also exchange its key material. After that, it will indicate, well, as for now, I'm done. Back to you, please. The client will also exchange some key material, and will then say, okay, we have exchanged our key materials. It's time to change the ciphers. From now on, everything I'm going to tell you is going to be ciphered or encrypted. I'm done for now. And the server will agree, will confirm this, and say, okay, everything I'm going to tell you from now on is also encrypted, and we're done. So with this handshaking process, the two systems can actually come to an agreement on how they are going to communicate with each other. And there's a few details here. For example, what systems typically do after they have exchanged their key materials is that they generate a new key, which is not based on public-private key encryption, but based on symmetric encryption with just one key that both systems will use. Why is that? Simply because it's cheaper in computation time. And because they first had this handshake and know that they can trust the connection, they can then agree upon a shared key to be used for a short period of time and use that for the rest of the encryption. And as I said, that's just cheaper, costs less CPU time. So, to actually verify that we have something that protects us from eavesdropping, it's time for another demo. Again, this is the packet sniffer. And now I'm going to use CURL again, but my URL changes to HTTPS localhost. Well, we still have the lorem ipsum, and we still have the laziness of me not wanting to copy-paste it. But this time, I'll try to scroll quietly. We're not seeing any data yet that is somehow readable. Okay, we can improve the pace a little bit because this is going to take some time. Well, here's some pieces that we can actually read because it's the certificate being exchanged. Okay, this is not really confidential, is it? The certificate is generated by a program called MakeCert. It's issued to me at Leonardo, which is the name of the machine. Fine. Nothing too special. Localhost appears somewhere. Lorem ipsum is gone. And that's a good thing, because anyone who was sniffing along our packages on the train Wi-Fi or the hotel Wi-Fi is no longer able to actually interpret them, to read what we are exchanging. So this is all fine and good. Means that it kind of works. We have encryption on the transport layer. Even if you can intercept the transport layer, no one will be eavesdropping on you. Cool. But as I said, we need three things. The second thing that we need is certificates. But what you just saw was certificates being exchanged. And what is a certificate actually? Well, a certificate, I think many of you have one actually. This is a certificate. In my case, it's a driver's license. And it actually says that the holder of this license, equals me, is allowed to do something. In this case, drive a car or a motor scooter thingy, I don't know. I never drive those. Never mind. I am allowed to do something. That is what it basically says. And in the context of computers, certificates are subtly different because they certify that you have something. Now, what does a certificate have? A certificate itself has a number, which is just there to identify it. It has a subject, that's me, who is the certificate about? Well, in this case, it's about me, but it can also be about a specific computer system. It has a validity, just like my driver's license, because it expires. It has a usage, just like my driver's license. I'm not allowed to drive a truck or a bus, but I am allowed to drive a car. And in the same sense, a certificate in a computer says that somebody has key material, but that's only intended for specific purposes. For example, it's intended to exchange, to build a secure connection, but it's not intended to identify the user. Just an example. There's a public key in it, of course, because that's what the certificate is about to prove. It's about proving that this computer system has a key. And there's a fingerprint algorithm on it, which is a way to describe how to derive the fingerprint, and the fingerprint itself is also on there, which is a mechanism to quickly verify that the certificate hasn't been tampered with. But what is also on my driver's license, no, it's not on my driver's license. On some certificates, for example passports, you'll see a signature as well. This certificate is useless as long as I'm issuing it myself. If I would say that I'm allowed to drive a truck, well, I can try to do it, and I'll probably hurt some people, and that would be the best outcome, I guess. So that's not typically a good idea to self-issue those certificates. And that's why somebody else is issuing it. And in the case of certificates in a computer, there's also another entity that actually issues those certificates, and that's also in the certificate, copied into the certificate. There's the issuer, that's who issued the certificate, and there's a signature from that issuer that actually says, yes, I approve of this message. And also for the signature, there's an algorithm. So that means we need something to create digital signatures, right? Well, luckily there's a diagram for that as well. This time the safe is working a little bit different. Imagine I want to send a letter to somebody of you. In that case, I would be using my private key to lock the safe so that it cannot be opened. Now, the safe is going to be put on a truck again because the pigeon didn't really deliver upon transporting safes. And the safe eventually arrives at your place. And now you can actually use my public key to open the safe. By the fact that the safe opens, you know that it was closed by me. And that means that you can trust whatever you'll find inside the safe to be my material, my letter, for example, to you. Now, this is fine. If the safe opens, we can be sure who closed it. Now, what if there's an evil guy or gal down there, and they want to send a letter to you and do as if it was a letter from me, but it is not? Well, they'll put the letter in the safe, they'll close the safe is transported to you, and you're using my public key to open the safe. This doesn't work, because the keys don't match, the safe doesn't open. And whatever you'll find inside the safe, if you were able to open it, at least it's not certified by me, because I didn't close the safe. Right? That doesn't make sense? So by assuming that the letter is from somebody and using their public key, you can actually verify that it came from them. A little bit more formalized, a signature is just a mathematical relationship between the message that it describes, the private key, held by me, for example, and the public key that each and every one of you is able to get from me. And this signature has a signing function. That's the thing that I apply. So I take the private key, I take the message, and the outcome is a value t. And you use this value t together with the public key and the message to invoke another function, which is called the verifying function. And if you invoke that function, it will either give you an accept, which means the signature is valid, it was signed by me, or you'll get a reject saying it's not signed by Maarten. So if you know the private key, you can create the signature. If you know the public key, you can verify it. And that brings us to the last thing that we actually need, which is certificate authorities. As I said, a certificate that is issued by myself and then presented to you is probably of not much worth. So we actually need a trusted third party. And those are entities that create those digital certificates. And those certificates certify that somebody owns a public key and that somebody is identified by the subject. That's all a digital certificate is. It says that somebody owns a public key. Of course, it doesn't say that this somebody owns the private key, because that can't be in the certificate. The certificate is public after all. Now, what basically happens here is, because I don't know all of you, and most of you probably don't know me, we need other entities in this game. For example, I can know John. John happens to know Alice. And you also know Alice. Now, I trust John. I don't only know John, but I also trust him. And John trusts Alice, and Alice trusts you. So by this trust relationship, I can trust you, or at least trust information that I get from you. Now, who is John? If I would look into my computer, I would pull up the keychain on a Mac, or I think it's called certificate management on Windows machines. And I'll find approximately 160 entities that issue digital certificates. That's 160 Johns. Let's be honest, I know none of them. There are a few companies that are pretty well known, but there's also a lot of companies that I actually never heard of. In fact, the only John I'm trusting is Apple, because Apple selected the list. And if you're running Java software, the John that you are trusting is Oracle. If you're running Windows, it's Microsoft. And I leave it to you if that's a legitimate decision to trust them or not. That's completely up to you. But they select the Johns, and maybe even the Alices, that actually built this whole system of trust. And that's an interesting thing, right? Did we actually verify this with whoever delivers our platform? I didn't. So approximately 160 of them. But the good thing is that those certificate authorities, as we usually call them, are companies that really take their business serious. For example, if their private key would be compromised, that would be an issue. So what they do is they have very verbose procedures that describe how they could actually replace their private keys. You can imagine that they are valuable, so they have large textbooks that describe how to do this. And typically a key ceremony is conducted in a room like this. You'll see that there's a bunch of video cameras in all angles of the room. There's people there in the front. They do the actual work. Then there's a few servers, and there's probably somebody who needs to go to a safe and get some tape or something where the actual key material is on. But what's also very interesting is that there's a bunch of people sitting here, and they all have notebooks. They're just writing along what's happening. They have a copy of the procedure with them, and they just check that every step is correctly being performed. Yes, we've done this. Yes, we've done this. Hey, there's a small derivation from the procedure. Are we all okay with this procedure? Yes, we are. Okay, everyone checks it. And some companies even go out on the street, recruit a few people with spare time on their hands to actually sit there and just check the procedures, because those people are recruited quite last minute, and you cannot influence them before to actually cheat and say that some step is correct while it was not. The video material is also published online afterwards. For example, this one's from Ayana. It's very interesting video material because these procedures take between 8 and 16 hours. And there's 8 cameras. So if you have watched all of Netflix, you can do this. It's absolutely amazing material. And in this way, those certificate authorities are sure that their key material, their private keys, still keep on being safe. And now we have time for a little fairy tale. What we see here is the beautiful city of Beverwijk. Who knows Beverwijk by any chance? Yeah, a few Dutchies probably. It's a small town north of Amsterdam. And once upon a time, we had a notary living there. You know, the people that actually pass your house buying contract or something. And this notary was like, hey, this digital certificate thing, I could make some money out of that because it's basically the same thing as I'm doing right now, but then digitally. How hard can it be? So they started their business, and that went actually pretty well. They did a good business. They earned a lot of money, but on one day, evil hurt their company. Like real bad. An attacker was able to use a file upload vulnerability on their public website. The public website was running .NET Nuke, and I'm not saying .NET is bad or something, don't get me wrong, but it was running on .NET. It was a file upload vulnerability, and they were able to actually enter the web server. On the web server, they found the password for that machine, but also for the domain administrator account. And using that, they were able to get shell access and actually traverse the whole network infrastructure until they found a machine where the private keys live that this company was using to sign their digital certificates. What does this mean? Really? No one? What this means is that all their digital certificates were, in one instant, useless. Because anyone could create a digital certificate that seemed to have been issued by them, but in fact was not. In the days after that, all hell broke loose, of course. Google blacklisted around 200 plus certificates in Chromium because they were issued by this DigiNotar company. Microsoft removed the DigiNotar root certificate from all versions of Windows that they had in support by then. Mozilla revoked the root certificate in all versions of Firefox. And Apple issued a security update to actually revoke the certificate as well. But some of you may have seen that there's a small asterisk down there. And this is where I'm not really proud to be Dutch. Because Microsoft issued this security update immediately, but there was one country where they didn't roll out the update. And you've guessed it, that country is the Netherlands. And you know why? One of the customers of DigiNotar was the state of the Netherlands. And all governmental systems were running on certificates issued by DigiNotar. And the government was afraid that if they would push this update to all their clerks and people that work for the government, those people wouldn't be able to do anything anymore. Some of you may say the difference isn't that big, but, well, let's not go there. Let's not go there. So, this update was not published to the Netherlands for a few weeks. It was withheld. And, of course, this reached the news. And the government member who was responsible for this said, people, there's no need to panic, not at all. It's very simple. If you use your web browser, just check that there's a green check mark, a green lock icon there, next to the address. If it's there, you'll be fine. Of course, this is not true. And this painfully depicted how few the government knew about what was actually going on. It's a bit as if you come home on a day and you'll find that the key, which was laying under the doormat, has been found, and somebody actually gained access to your house. The key is laying under the doormat because you have a cleaner that comes by twice a week to clean your house. And now you can do two things. You can immediately replace the locks because somebody obviously found the keys, but instead you're like, oh, but wait, the cleaner comes tomorrow, and they need to be able to get into the house, so I'll just leave it this way, because otherwise my house isn't clean. Yeah, but there's somebody who can actually come into your house and you won't even notice. Well, what eventually happened, and which would be the right approach, is to update certificate revocation lists. Those lists are issued by all certificate authorities, and they contain a big list of all certificates that they want issued and signed, but should not be trusted anymore for some reason. For example, because the private key was compromised. And in this case, DigiNotar could just easily put all the certificates that they ever issued on this list. So, small demo, because you might think, okay, now if we have this green lock icon, everything's fine. Not particularly. Here I'm running a website on my Mac, which is called google.nl. And Chrome will say, just to zoom in a little bit, that the connection is secure. That's because I have a certificate authority on my Mac, and it issued a certificate to google.nl, which is then copied into my host file to map to 127.0.0.1, which is running a web server that will just proxy google.com itself. And you can see that because it actually thinks I'm in Belgium. Well, that's correct. So it's really running a google.com. And I can actually refresh the page if you really think I'm faking it all. It's still there. So what we now know is that we are talking to the server that we think we talk to. But take care, because the only truth is down there. It's not in what you see here. It's in what you see in the address bar, or what you see in your program code when you connect to some server or some host. And this has actually been used by some attackers to make up websites that have like Unicode weirdness to look as if it was google.com, but it's actually other characters, and they just look the same, and then they try to get your credentials. That's also why we now have extended validation certificates, or EV certificates. Those are issued by some of the certificate authorities, which do a more thorough check on who you are and actually come to your office, ask for your government ID, ask for your Chamber of Commerce papers, ask for a signature of the person that actually run the company, and then you'll see in the address bar that it's validated to be the company, the legal entity that you think you're talking to. And some companies in the Netherlands use that. Some companies outside the Netherlands, by the way, also use that. So you can be actually sure you're not only talking to the correct address, but also to the correct organization behind it. So to make it a bit more practical in the last minutes that we have, here's a few tools and tips and tricks that you can apply. First of all, if you want to debug a connection, I personally love CURL. Giving it the -v switch will allow me to see a bit more detailed information, and I can also say -k, which says, okay, for the time being, please do not validate the whole certificate chain. This can be useful if you have, for example, certificates issued inside your organization and you don't have the organizational certificate that actually signed them. Of course, you should actually get that one, build it, and use that to validate the connection that you're building. But if that fails, you can see if it would succeed without. Now, if you want to troubleshoot a little bit deeper and see what's actually going on, see, for example, what certificates are being used to build up the validation path, you can use the OpenSSL command line tool. It has an S-client command, which is socket client. We give -show certs, -server name, and then the name of the machine that we want to connect. This is there for SNI purposes. Then we give it the -connect command, and we specify an address, either an IP address or a host name. and a port number. And it will give us a lot of information about how the connection is being built up. If the connection cannot be built up due to, for example, protocol version errors or cipher errors, you can use Nmap. It has a built-in script called SSL enum ciphers. See, it's SSL, by the way, it's not TLS. You can tell it where to connect to, and it will just attempt all known protocols and ciphers to build up a connection. Don't do this on systems that are not yours, because many security intrusion detection systems will actually think you're a hacker if you do this. They'll consider this bad, and well, maybe some firewall rule will kick you out immediately. Don't say, I haven't warned you. So if you're running Java software, we're on a Java conference after all, with Javax NetSSL Trust Store, you have a mechanism to say to the JVM, this is the file that contains all the certificates that you should trust. By default, there's a trust store shipped with your JDK or JRA. Its password is change it. How original, how convenient. But you can supply your own trust file. Give it a different password if you wish. And then the system will refuse connections that cannot be validated against the certificates in the trust store. There's also a key store, which is more or less the same thing, but then for private key material. And it also has a key store password system property that you can use to give the password for that file. And the key store is there to contain keys, right? Does make sense. Those can be the same files, by the way, but it doesn't have to be. Next, there's a way to actually debug what's going on transport level by using JavaXNet debug equals SSL, and optionally you can also supply a flag to filter out a bit. I would recommend to do this because this command will really give you an enormous amount of output. And finally, if you're working with key stores, I would recommend using a tool like Porticlay, which is a graphical user interface to build trust stores and key stores. You can do it with KeyTool, which comes with the Java platform, but that's not a very convenient tool. Porticlay is just a graphical user interface, which allows you to inspect certificates, generate keys, etc., etc. So, before you leave the room, there's a few public key takeaways. First of all, don't use SSL anymore. Don't use TLS 1.1. Use TLS version 1.2 or 1.3. Second, if you are using transport layer security, take care in whom you trust. By default, there's 160 Johns, and you probably don't trust all of them, especially not if you're running secure communication inside your organization. And finally, when in doubt, when in trouble, open your toolbox and know how to use it. Tools like OpenSSL, CURL, Nmap, Porticlay can be very convenient to actually pinpoint what's going on and be more successful in building this connection. And with that, there's a little bit of room for questions, if there's any. And other than that, I would wish you a very pleasant continuation of DevOps. Thank you. There is a question, and I'll try to repeat it.
Okay. Yes, the NSA probably will soon have quantum computers, and then they can break RSA.
That's right. The NSA, or whatever government secrecy agency, are working on quantum computers. And those quantum computers promise to be more powerful when it comes to finding those prime factors that we talked about, the P and the Q. There's also being academic research on post-quantum cryptography. This is not covered in this talk, as you might have mentioned, but there is work being conducted on that to make encryption algorithms that are less vulnerable to the power that quantum computers actually bring us. On the other hand, as far as I know, there's no quantum computer yet capable of cracking, for example, a 2048-bit RSA key, which is a bit of the default currently. But, well, maybe somebody has, but they just didn't publicize it. You never know. Any other questions? Great, thank you.